Okay, so I guess we can start the afternoon session, which will consist of 3 talks. The first of which will be by Sally Shrapnel from the University of Queensland, and she will talk about causal discovery in the quantum context.
Thank you, Julia. Thank you to Thomas and Fred and the organisers for inviting me to give this talk. I'm really very grateful to be able to be here, and particularly grateful to be able to be here in person. My university gave permission for staff members to travel literally 2 weeks ago. So it was very touch and go there for a while. I thought I was going to have to do this by Zoom, but I'm very glad to have been able to come. It's been a really terrific interdisciplinary workshop. I've enjoyed talking to philosophers and economists and statisticians and biostatisticians. I've learned an awful lot about classical causal modelling and causal inference. It's been really very useful for me. So I am aware that this is the third talk that you've seen this week on quantum causal models. And there is a fair bit of overlap between the talks that Eric gave and John gave and the talk that I'm giving. But I thought that I would try and come at it from a different perspective. And that is, I'm really speaking to the people in the audience who know nothing about quantum. So the idea is that I will try as best I can. At the end of the talk, hopefully you'll have a bit of an intuitive idea as how the quantum causal model works, maybe some practical examples of where it would be useful. But most importantly, I'm hoping at the end that you may see some opportunities and avenues for being able to contribute to this field. So first of all, I'll just be giving a little brief overview of the problems that we have when we try and apply classical causal methodology, just kind of prima facie to correlations. And we've seen this, so we saw it in Tim's talk a bit, and we saw it in Eric's talk, and we have seen this to some extent. So I'll go through this fairly quickly, but I'm just giving my 2 bits worth on the way that I see the kind of 2 key problems. Then I'll be talking about a particular quantum causal modelling framework, which is work that I did with Fabio Costa in 2015. And then we'll be talking about progress on quantum causal discovery algorithms. Now, a bit of a spoiler alert. So I know that in the classical causal modelling, there's a vast taxonomy of causal discovery algorithms. You've got score-based methods and constraint-based methods. And I think Daniel was like 4 hours worth of tutorials or 6 hours or something. So we're going to get through quantum causal discovery in about 15 minutes. There's one algorithm that's been written, and then there's a couple of kind of exploratory avenues that people are exploring, but this field is wide open. There's a lot of things, and so I will be ending up really with more open questions than anything, and hopefully you will see some avenues for where you can contribute. So what are the problems? Well, typically we come at understanding the problems with applying classical causal discovery methods in quantum experiments from the Bell experiment. And as you know, you start off with entangled particles, you send them to labs that are very far apart, space-like separated labs. And then you have a choice at either lab of doing one of 2 measurements. And each of those measurements, you get a binary outcome. And that binary outcome is random. And if you set up the experiment so that when you choose the measurement option, whether you do measurement 1 or 2 here and measurement 1 or 2 over here, if you randomize that, then you get these independences. So the settings are marginally independent because you're just randomizing them. And then you have this no signaling conditional independence. So that is the outcome on one wing is independent of the setting on the other wing, given the setting on your own wing. And thank goodness for this in a way, because if we did have the faster than light signaling and everything would change. Like really everything would change. So in a way, the no signaling in some senses, saves you from some, I guess, difficult questions. So the problem is when you plug in these conditional independencies and when you think about the kind of constraint-based methods, you can show that you can't produce an explanation of the DAG that's both Markov and faithful. Now, Tim talked about unfaithfulness, and maybe unfaithfulness is okay. And I remember earlier in the week, someone said, we accept unfaithful explanations all the time in the classical world. When there's feedback mechanisms, when there's homeostatic mechanisms, and we're just not sampling at a rate that's fast enough, then unfaithfulness is something that we are willing to accept. It obviously causes problems for causal discovery. But the problem in the Bell scenario is that the the fine tuning comes with a whole lot of other problems. So if you're going to posit these kinds of fine tuning to make sure that your conditional independence holds, then you've either got to accept that causal influence can travel faster than the speed of light, yet somehow we can't use it to signal. We can't actually get hold of variables and control them. Or you need to posit retrocausal explanations or accept superdeterminism. And there's a lovely paper. I really like the paper by Clark Gleamore that he wrote about this. I think if you haven't really fully understood the weight of the Bell correlations, that's a really good paper to start with. So the second problem is the fact that we don't have this really lovely distinction between interventions and observations in quantum systems. So typically in the classical causal modeling world, you know, we have this thing where, like, if you've got all the interventions, if you can do all the interventions, then recovering the causal DAG is somehow easier. And typically what we hear is, well, there are situations where interventions are unethical or they're difficult or they're expensive, and therefore we're resigned to doing causal modeling when you only have this passive observational data. It's very difficult in the quantum setting to understand what passive observation means. So, you know, there are many ways that you can see this, but I, for one, accept the fact that quantum systems just do not possess objective properties that can be assigned prior to and independently of the act of measurement. And it's not as simple as just that, well, it's just ignorance, and if we could measure it somehow more precisely, we'd be able to understand what was going on. It's much more complicated than that. You can look at the literature on contextuality. You can delve into aspects of the Heisenberg uncertainty principle and look at it in various physical situations. You can go to the ontological models framework. There's lots of literature out there to help you explore that question. And for my talk, I'm not going to explore that question. I'm just going to accept that is a problem, that we don't have this ability to do passive observations. There is, of course, you know, people sometimes say, well, you know, you can prepare something in an eigenstate of an observable, and then you can know with certainty what the outcome is. So if I went to Julia, who's an experimentalist, and said, Julia, can you please, you know, prepare me a quantum system in a state, you know, that's an eigenstate of a zero outcome, she can give me that. And I know with certainty, if I measure that system, I will get a zero outcome with certainty. But the thing is, if that was all you could ever do, if you could only ever, you know, prepare systems in eigenstates of observables and measure them in that basis, you wouldn't see the kind of correlations that we find interesting in quantum systems. So again, I set that aside. So I think this leaves us with a really interesting puzzle. So on the one hand, it seems like we can't shoehorn quantum correlations into our understanding of classical causation. But yet there are growing armies of quantum engineers all around the world who are building really sophisticated devices that are made of components that they can exchange. They can intervene and change these components. They can make counterfactual statements. If I turn my laser to this instead of this, here's how the outcomes would have changed. If I put a beam splitter instead of a half-wave plate, this is what would have happened. So there is a sense in which quantum engineers are already using causal language and making causal decisions, and perhaps even having causal explanations. So I've just put these three examples up. These pictures are from the University of Queensland, where I work. This is Dr. Sarah Lau here on the left. She's an experimentalist who's she's now a postdoc and is working with a quantum optics setup there. That's Dr. Katch Alexander down on the left-hand side. She was also a PhD student with us, and she built the world's very first quantum light microscope. So when you use light to try and look at a sample, if you want to improve your resolution, you have to turn the power up. And if you turn it up, eventually you'll fry the sample. That's not good. But you can use quantum light so that you can have incredible resolution at very, very low power. And that's enabling us to see biological samples now at a resolution that we've never seen before. So Katch and the team are there working with that microscope. The top left-hand picture there is 100 microns wide. And that's Professor Helena Rubinstein-Dunlop, and her team has created a Bose-Einstein condensate, which they can control such that they can make these beautiful little pictures of whatever they want. There was a kangaroo or the Mona Lisa, but I thought I'd stick with the gender theme for that picture. Anyway, so So thinking about that led us to develop these quantum causal models. And really, at the most abstract level, these quantum models are just what quantum engineers do and use all the time. And you might think, well, what's the point? There's already people out there using this kind of framework. Why do we need to call it causal models? And why do we need to kind of explore this? But really, it's the same as in the classical case. It's really nice having an abstract formalism that's independent of the platform that you use. So whether you're using superconducting qubits or photons or this kind of application, it should be agnostic. So just as in classical world, you can use causal models in economics, or you can use them in medicine. We want that kind of agnostic framework. And so what I'm going to present is based on the paper that Fabio and I wrote. If you're interested in philosophy, I wrote a kind of philosophy version in the British Journal of Philosophy of Science there. And then if you want the really wordy version, there's my PhD somewhere on the internet. Right, so when you construct a quantum causal framework, there are two principles that we wanted to retain. The first one is this principle of independent causal mechanisms. And this is a quote from the Elements of Causal Inference, a textbook that I love, which says the causal generative process of a system's variables is composed of autonomous modules that don't inform or influence each other. So you have this idea, that the edges in your DAGs, they don't affect each other. They're somehow independent. And there's this kind of Lego block idea of the way you build causal structures. So you might have a joint probability, but it will always decompose into these sets of conditional dependencies. And that these conditional dependencies are due to these independent causal mechanisms. So we're going to try and retain that kind of principle. And we also want to retain the principle that says that we have to allow the possibility of causal discovery through local intervention. So I don't want to be positing things that I can't do experiments to uncover. I don't want to be positing potential causal influences where there is some in principle reason why I can never see them, okay? And these two kind of, in a way, give you the fact that all correlations need to be explained causally. So this is kind of the summary slide. For the mathematics of quantum causal modeling, you really only need two equations, right? There's this one, which is the causal structure. So W is the process matrix. It's a matrix, and it will give you ultimately what the causal structure is because it factorizes into tensor product factors, and each of those factors represents a causal mechanism. And the other equation is, how do I attach probabilities to this story? Because ultimately, we're working with correlations. And so the bottom equation says the probability of a set of events occurring at each of your nodes is given by this formula, and we'll unpack that. Okay, so ultimately what we're going to be getting to is these two, so that you understand what these two equations are. It's a very general formalism. So you can think of the nodes as kind of space-time regions where you perform your interventions. And so, for example, A might be, Alice in a lab here in Berkeley, and B might be Cindy in a lab in Sydney. And let's say Alice and Cindy are performing quantum operations in their labs, and then they're sending information to each other, quantum information, let's say via a photon, an entangled photon, something like that. So the nodes can actually represent those kind of spatial locations where you do your interventions, and the edges can actually be the system kind of traversing and passing on information from one node to another. You can also actually think of them in a kind of more in a smaller sense, in that they could be gates in a quantum computer or little elements in a quantum computer. Just anywhere where you can make a change or perform an intervention can account for the nodes. So I'll start with the circuit model, and I thought long and hard about where I should start. And I think really the circuit model is an easy place to start because it's often now where people get introduced to quantum theory. So all the big companies like Google and IBM and Microsoft, if you go to their quantum page now, they will all have introductory tutorials for people, computer scientists, statisticians, people who know nothing about quantum. They're really good introductory tutorials, and they always start off with the circuit model. This is kind of the Bible of quantum information. It's a fantastic book. You read the first 3 chapters of that book and you understand all the maths that you need to know to understand quantum causal modeling. It's all kind of linear algebra and discrete Hilbert spaces. So the circuit model, it's very similar to a classical circuit model. You prepare a state, can be a bit, a single bit if you're in classical computing, but if you're in quantum computing, it's a qubit, can be in a 0, 1, or a superposition of those. And then you perform logic gates. They can be single qubit logic gates or 2 qubit logic gates, or as many as you like. And so the main difference is you have these, is there a pointer? Oh, you have the entangling gate. So the U with the lambda on it is a gate that's entangling those 2 qubits. And at the end, you perform a measurement. Okay. So there is obviously an idealization going on here, and that is that the wire represents the identity channel. So that is you start with a system, you prepare it, you then wait a bit and perform your gate. And when you're waiting a bit, you don't want anything to change. So that's obviously why we represent it with the identity channel. And all the gates can be represented with unitary operators. Okay, so unitary operator, just a unitary matrix. So what we want when we go to the causal modeling formalism, at the very least, is we kind of need to be able to represent, we need some mathematical object that can represent these kind of operations. So preparations, measurements, unitaries. And so what we do is we use completely positive maps. So when you think of events in a classical causal model, you think of a random variable where the values give you all the possibility space for, the modeling that you're doing. In the quantum case, we have a kind of different notion of an event, and that is all the available information that's available to you at that spatiotemporal location. And we represent them mathematically by completely positive maps. So these CP maps will map operators, positive operators, over the input space of your node to operators over the output space of your node, and you index them by both the choice of your quantum instrument, I'll get to that in a sec, and also the respective outcome. Now, I realized after speaking to some people after Eric's talk that we use the word instrument all the time in our quantum talks. It's nothing to do with instrumental variables. Like it's a completely technical quantum term. All it means is it's a set of completely positive maps that sum together to be trace preserving. And the way you can think of it is, so, when we think of the Bell experiment, you've got Alice and Bob, and Alice can choose one of 2 measurements. That measurement choice is a quantum instrument, and you describe the 2 outcomes. So when she chooses one particular measurement, she'll get one of 2 outcomes. Each of those outcomes can be associated with a completely positive map. So for each of those measurement choices, the 2 CP maps can sum together to be a completely positive trace preserving map. And the trace preserving property is kind of like normalization. It just ensures with probability 1 that you're going to get something, that you're going to have one outcome. Okay, and why complete positivity rather than positivity? Well, systems combine using the tensor product in quantum mechanics, and we want to be able to share entangled systems between the parties, and we want to maintain positivity. So we request complete positivity. So in the quantum causal modeling frameworks, you've seen this in Eric's talk and also in John's talk and now in mine, we use this isomorphism. Instead of representing the CP maps as a map from an operator on one space to an operator on the other space, we put those 2 spaces together via the tensor product, and we represent the map as a matrix on that combined space. Why do we do that? It's really just mathematical convenience. I have thought about whether there's some deep philosophical reason why that's a good thing to do. I don't think so. I think it just means that we can perform the trace operation so that we can trace out part of a channel and get identity on the other part of the channel. So the Choi-Jamelkowski isomorphism is just to make that explicit when you're dealing with the matrices. Although I'll be interested to hear in the question if there's anyone in the quantum community that can think of anything deeper than that. Okay, so as I said before, nodes are defined by these possibility spaces for the many ways a quantum state can change as a result of a local intervention. And the nodes of the graph are then associated with regions where we can perform these quantum instruments, or interventions. So just think of instruments and interventions as interchangeable. So as I said, interventions are characterized by quantum instruments. They represent the collection of all possible events that can be observed, given a specific choice of probing the system, like choosing a particular measurement outcome, doing a unitary, for example. So that's a deterministic instrument. So if you perform a unitary gate, If you prepare a system and then do a transformation and then measure it, you can also represent that using these CP maps and CPTP maps. So mechanisms are responsible for the evolution of the state from the cause to effect nodes. We can ask, we can go, I guess, philosophically, if you want to, in the same way as you do in the classical case, you can say, well, let's assume that there's some underlying deterministic causal structure that generates the correlations. And the reason that it's indeterministic is because there's some noise. You can do a kind of similar thing where you say, well, it's unitary operators that are responsible for the causal mechanisms. So you might have, out of Alice's lab, we have, Rho, she performs some operation. We then apply the map to Rho, so you get some new state. And then during the trip to Bob's lab, there's some evolution that occurs, and you end up with sigma, a new state coming into Bob's lab. But if we assume that there is this existence of unmodeled noise, and noise in the same way as you do in the classical case, you don't want it to be correlated. If it's correlated noise, then it's going to like kind of act like a common cause, and it's going to undermine your principle of independent causal mechanisms. You're going to have causal mechanisms that can be correlated. So if you assume that there's unmodeled local noise, then the causal mechanisms are also represented. We just use the CPTP maps. There's a slight difference of a transpose, and as Eric said in his talk, it's really just to keep, when you're accounting for probabilities, it helps things work out neatly. So causal structure itself is defined by combinations of causal mechanisms, these quantum channels, that connect the nodes and are responsible for generating correlations between them. So we can define a positive semi-definite matrix, W, which we call the process matrix, on the tensor product of all the input and output Hilbert spaces of the nodes. And we call this the process matrix. So all the information regarding the way the different channels connect the nodes in our DAG is encapsulated in this process matrix. I put a little star there because I call it the process matrix, but this is an object in quantum information that's come up in different contexts, and it's called different things. So I called it process matrix because I came across this object working with Fabio, who was part of Czeslaw Bruckner and Onya Nareshkov originally wrote this paper on indefinite causal order. So this is relevant to Julia's talk, where you imagine a space of process matrices where you don't require this independent causal mechanism idea. You say, okay, all we're going to have is local quantum mechanics to be true, where you perform interventions, but anything goes outside those local labs. And if anything goes, and you just have sensible constraints on the process, like it needs to be positive semi-definite, and you need to be able to, if all the probabilities need to sum to 1, etc. If you have those constraints, then it allows for some more exotic things like the indefinite causal order, the quantum switch, where you have a quantum degree of freedom that kind of switches between different mechanisms. So the process matrix allows for all those possibilities, but in the quantum causal modeling framework that I'm presenting here, we're limiting ourselves to the subset where the causal mechanisms are independent. But there is also the quantum comb formalism. Giulio Hirabella and the group at Pavia use that. It's the same object as the process matrix. The process tensor, Kevin Modi, who's a physicist at Melbourne and Monash, he also uses this object. And I think his work's often overlooked in the quantum causal modeling community, because typically what they do is they just look at a single quantum system at multiple times where you're doing interventions, and then looking at the way there's correlation and non-Markovian effects. But it really is the same kind of object that we use. And so I'd encourage anyone who's interested in quantum causal modeling from the quantum community is to keep an eye on Kevin's stuff. They're really prolific. They put out a new paper every 3 months or so. And then I think John and Rob Speckens and those groups refer to this object as the quantum state, quantum causal state, I think. Correct me if I'm wrong, Ellie. Is that right? Quantum causal state. But I'm going to call it the process matrix for the remainder of the talk. So the important point is that if all the relevant quantum causes are included in your model, then the process matrix should decompose into a fixed set of independent quantum channels. And the structure will hold regardless of the interventions that you do at each node. So we retain this intervention invariant property that you have in classical models, and we'll call this process Markovian. So how do we attach probabilities to this story? Well, as you may or may not know, there is a Born rule for how you attach probabilities when you have single quantum systems. So if you have a single quantum system that you prepare in a quantum state row, then the probability of getting a particular outcome is given by the trace of the measurement operator and the density matrix of that state that you present. The process rule is a generalization of this. So what it says is that the probability for a sequence of events, so a set of events at your nodes, is given by the maps associated with the interventions that you choose, tensor product, with the process matrix, and then you take the trace, and that gives you this joint probability. So correlations are just multilinear functions of the completely positive maps at each node. Was that 15 or 10? Oh, 15, good. Okay. Is it a unique rule? Yes, if you believe in non-contextuality and contextuality. If you think that's important, you can prove this. One way to say it is that if a CP map can be realized by two different instruments, so if you've got one kind of measurement, another kind of measurement, and you've got one CP map that's shared by those two different instruments, then the probability with which you assign should be independent of the instrument that you use. If you want to understand more about that, you can read this paper. But for me, that says this is the appropriate rule to use in this situation. So if all the correlations are determined by causal mechanisms, it implies a set of linear constraints, and it literally is that tracing out different subsystems and getting kind of partial traces and marginalization of the process. And this is what presents us with the opportunity of defining analogues of the Markov condition and faithfulness. So now we get to the causal discovery, luckily, because I've got 15 minutes left. So these were some possums that got into our optical experiment in Queensland one day. But the thing with causal discovery is we know that the structure of the DAG is contained within this process matrix. So how do you get it? How do you get the numbers to put in that matrix? You actually have to do lots and lots of instruments. You have to perform lots of interventions at each node. How many? Well, it scales like everything in quantum mechanics. It scales really unpleasantly. So we have to use these things, informationally complete instruments. You can think of them as you have to do enough operations to kind of span the Hilbert space that you're exploring, the tensor product Hilbert space. And so the scaling is exponential in the number of nodes. So every time you add another node to your DAG, then you have to do a heap more operations. So any Markovian process is composed of three kinds of tensor factors: the input channels, the intermediate channels, and then the output channels, where you know, it's like a measurement, you're actually discarding the system. And so the way the causal discovery algorithm works is it actually looks for this order event by tracing out, starting at the top, looking for identity on an output. And then once you find which nodes are last, you then take them out. And then you look for identity on the next set and you trace them out, and you do this kind of piecewise until you get to the causal inputs. So the input to the causal discovery algorithm, which Cristina Giamazzi and Fabio Costa developed in 2018. Cristina's a postdoc at the University of Technology, Sydney now. And she developed an algorithm which you can download for free from GitHub. You need to input the process matrix. You also need to input the number of systems that you're working with and the dimensions of them. And then it will determine, first of all, is the process causally ordered? And what I mean by that is, are there independent mechanisms, or is there like a switch? If there's some quantum degree of freedom that is switching between different mechanisms, the algorithm will say, sorry, can't go any further. So if it's causally ordered, if it's not causally ordered, it will reject. If it is causally ordered, then the next thing is it will output the sets of nodes that can't signal to each other, that are independent. And then it will check if all quantum variables are included. If all quantum variables are included, then it can output a unique DAG. If there's not, so if there is some non-Markovianity, it will tell you there is non-Markovianity, but unfortunately it can't tell you where it is. So it just says there is a quantum hidden common cause, but there is no algorithm yet to identify where that is. So would you ever use this? Well, for small numbers of systems where you can actually get the process matrix by doing your tomography, it's useful. So this is kind of state-of-the-art quantum internet at the moment. It's got 3 nodes. So at the moment, it is still in the realms of where figuring out what the process matrix is not terribly onerous. And perhaps this could be useful for verifying the order of local operations. If you're needing to make lots of operations fairly quickly, the connectivity structure possibly. But I think what we will see, I mean, quantum technology is a multi-billion-dollar industry, and we will see more and more complex quantum engineered networks and systems in the future. And this kind of cool technology ultimately, I think, could benefit from some ability to do causal inference. So to be able to identify when you've got quantum noise, for example, that's non-Markovian and affecting your experiment, when you've got an order of operations that you want to be able to verify, when you want to be able to verify the connectivity structure if it's dynamic and changing. And so in those situations, we really want to try and think about, is there some other way that we can estimate the process matrix without needing to do this exponential number of interventions? And so we've just had a few kind of little gentle probes in some interesting directions to think about this. One is, well, let's just construct a database of process matrices. So let's just simulate them and then use machine learning to classify, to distinguish between them. So then, you're in your situation and perhaps you have partial knowledge of your process matrix. You don't do all the informationally complete instruments, but with machine learning, can you then adjudicate between which process is that you're closest to? So how much time have I got, Julia? Like 2 minutes or something? 9 minutes. Oh, good. Okay. So we did this in a simple setup. We just had a single quantum system. It was a qubit, and we applied 3 unitaries at different time steps, and then we did a measurement. So ordinarily, to reconstruct the process, you'd have to do kind of measurements either side of each of the unitaries. But what we wanted to do is to see whether we could learn anything about the process in the absence of that tomographically complete information. So we just simulated a heap of different processes with different, either Markovian processes with different dimensions, so 2, 4, 6 dimensions, and then a whole lot of non-Markovian processes of different dimensions. And then we just threw it all into a random forest to see whether it could estimate if you're just given the measurement outputs conditioned on which unitaries. So what you feed the algorithm is, I did this unitary at step 1, this unitary at step 2, this unitary at step 3, and here's the probabilities of the outcomes that I got. Then the algorithm says you have a non-Markovian environment of 4 dimensions, or you have a Markovian environment of 2 dimensions. How useful is that? It doesn't tell you exactly what the problem is, but it kind of tells you the scope of the problem. You've got a really big non-Markovian environment that's affecting things. That's something that might be useful. Yeah.
Does the algorithm also return a construction in case it tells you, look?
No,
okay.
It should, but it doesn't yet. Next stage. Yeah, so that's just what I said. And then the next step was to say, well, could we do this kind of from using well-controlled experiments instead? So, could you have a situation where, for example, the physical setup, and then you simulate physically using your experimental equipment, you kind of simulate Markovian correlations, or you simulate non-Markovian examples. So you introduce a kind of extra qubit that's going to generate correlations, and then you use that experimental data to classify future experiments where you don't know, where the kind of hidden common cause, for example, is unknown. And so we did an experiment with Kalmudi where we did that, just characterizing non-Markovian classical noise in a quantum optics experiment. So there is some other work. Gao, Kevin Modi and Paletti put out a paper where they use tensor network-based machine learning. So tensor networks are a kind of machine learning that was inspired from the quantum community. It is essentially also a supervised learning technique. So they generated a database. I guess the key thing that's interesting here is that you can represent the process in a more compressed form using matrix product operators. And there is a bit of a tradition, not in the quantum causal literature, but in other quantum information literature, and using matrix product operators as a way of representing quantum processes in a more compact way. So that's another area that needs to be explored further. And then Giulio Curabella's group has also put out an algorithm. And as far as I can tell, it really just follows the algorithm that I presented earlier, that Christina presented, but instead of getting the process matrix by doing all the informationally complete measurements, you actually choose which order you do the measurements in based on that tracing out procedure. So you start with nodes, and then you do the tracing out and see if on each other node you get the identity. And when you find a node where you get the identity, you go, okay, so they're causally connected. So it's a kind of systematic way of reproducing that process matrix. The nice thing is that they're able to prove by doing it this way that if there's low noise, if it's low rank, if it's sparse, basically, then you can do this fairly efficiently. Okay. So I guess, I hope what I'm leaving you with is all these open questions. Like, there's a matrix that we need to be able to estimate. There, I'm sure, are many techniques in machine learning that are better motivated, maybe sequence to sequence learning, things like that. Maybe G-flow nets where you're learning a graph and a sequence. I'm sure there are better motivated machine learning techniques that we can use. There's a lot of structure in the process matrix, and in the methods that I described, we're not really exploiting that structure. There are, I'm sure, methods that we can use to do that. No one's thought about score-based methods in this context at all. That's something that should be explored. And there are probably physical scenarios that we're more likely to come across in quantum technology that are going to place constraints on the process that will make it easier to learn and discover. And with that, I thank you for your attention.
Questions?
Thanks for the really great talk. I was wondering if it's sort of related to your score-based question at the end. Is there a sense of goodness of fit given? So if you fix a structure,
yeah,
and the process matrix decomposes in the way according to that structure. I guess as someone who doesn't know what the data actually looks like, I'm not really sure what it means to say I have like an estimate of that process matrix W hat, and I want to know whether it's a good estimate given the structure that I've just.
Yeah, it's a great question. And I think that, well, no one's really explored it. I'm sure that there are measures that would accurately reflect a goodness of fit. I suppose one way to think about it is with Christina's algorithm, there is a tunable parameter which kind of accepts a degree of noise in it, because what we're doing is we're tracing out part of your process matrix and looking for identity and looking for that kind of perfectly. And obviously that there's some noise limit that you might want to tolerate. And you want to be able to tolerate it locally rather than kind of smeared out over the whole causal structure. So there's probably something in terms of using score-based methods where it's a score kind of for each local area rather than for the overall process. Because I would worry if you just used a score-based method for the overall process that the noise might end up kind of being smeared out and you'd miss a hidden degree of freedom. Does that make sense?
Yeah, insofar as I understand anything, but maybe because it decomposes in this local way that it's like basically like something given the parents.
Yes.
Then maybe you only need that local noise.
Yes, I'm sure that's right. I'm sure that's correct. That's probably the right way to do it. Yeah, thank you.
Thank you. Can you say a little bit more about the underdetermination of the structure? So you said somewhere along during the talk that under certain conditions you would get the unique DAG out, presumably because you're doing all of these sort of interventions there, but then in the non-Markovian case, then you can't say much. So could you, I don't have a good sense of this sort of space. Could you explain that a little bit more, what the underdetermination looks like then structurally?
Yeah, so I think it's probably possible for you. Well, let me think about it. I think the worry is that, so here's the way I'd put it. In the process matrix, so as you know, the process matrix is composed of these tensor products of these local channels. So it should be, if you have just one node, one hidden quantum node that's correlated with maybe two other nodes, and you don't know, then it shouldn't affect so much of your process matrix. It should only affect those parts where those tensor factors are involved. But if you had a node, for example, that was correlated with everything in your model, it would change every aspect of the process matrix. It may only change it slightly. So therefore, I guess there is that underdetermination. But as Daniel's saying, maybe there's enough of the structure there that with some thresholding, if you assume some thresholding of how far from the identity you're willing to tolerate, maybe you can resolve some of that underdetermination. That makes sense.
So just one really nice talk. One question I had relating to Jonathan's talk this morning was he had these graphs, and then when the operator was invertible, he could flip them around. And obviously, from a kind of causal discovery view, that was really weird because you'd be turning a non-collider into a collider. So I don't know whether it's maybe a very basic question for the quantum people, but can you share any light on that?
It's not a basic question at all, and I'm not sure I can say anything intelligent, but I'll give it a go. So I think the unitary story is reversible. And if you assume that the causal mechanisms underlying everything is unitary, then what is it that gives you the causal directionality? And I would say it is the interventions. It's the possibility of interventions and the fact that when you do an intervention, it signals, and that the interventions are CP maps and CPTP maps, and they can be indeterministic. So that's kind of where the indeterminism comes in, and that's why you don't have that problem. I would say there is a difference between, so John's formalism, so as I said, our process matrix has to decompose into these tensor factors. And for him, he also allows channels to be commuting rather than necessarily factorized into the tensor product. So his definition of Markovianity is broader. It captures commuting channels, but I'm not sure how you do causal discovery in that context, which is why I'm kind of still stuck here. And I think even when you have commuting channels, you still need to think about, so what's the intervention that I can do to disambiguate? And I think once you start thinking about where you do the interventions and what you have to do, it kind of naturally falls back into that tensor factorization language. So that's why I kind of default back to that, even though John's version is more general. I'm not sure whether that has implications on that reversibility statement. John's the person to ask.
Okay, great, thanks.
Maybe just I wanted to ask a follow-up to this, and then I'll give you the microphone. I was just wondering if, in the attempt to make the model more strong to noise and etc., is there any limitation that one shouldn't do to this intervention nodes? For instance, maybe sending pairs of entangled particles that could perhaps alter the causal model underneath. And
so are you asking? So certainly there would be, I guess, if you did something like a switch, and if you do anything, and I think a lot of the experiments that you've designed and the work that you've done, it would be difficult to uncover the processes, because what you are doing is you, in a sense, this independence of causal mechanisms is no longer there. So I think you're right. I think it does make it difficult. And so there probably is a restricted set of operations that you can do. So I think if you have any kind of qubit that's going to, change your causal structure, if you're conditioning on that, then I think you'll find it difficult to use this methodology.
Yeah,
Yeah.
Thanks.
And just before Isaac asks his question, I did forget to make one comment. In other work, there will be other work appearing on the archive soon. So Isaac is working on causal discovery, quantum causal discovery using category theory. So keep an eye out for that. Anyway, your question.
I think, well, there's a problem that I'm not very familiar with Modi's stuff on quantum non-Markovianity.
Yep.
But a thing that that I was discussing with Ellie the other day is from around the time when you first wrote the paper with Costa, these experiments from Perimeter where they were figuring out how much of a correlation between two time-separated quantum systems was due to prior entanglement. There's a kind of, in some sense, special quantum effect where common cause from prior entanglement helps you. You can tell more about common cause that was due to prior entanglement than you can in a classical setting tell about common cause that was due to ordinary correlation of random variables.
You talking about Katja-Reid's what?
Yes.
Yes. Okay. Yep.
And so I was wondering whether like how much of the non-Markovianity or how much of the causal discovery protocols rely on the general insight from that work, which was basically that when you have a common cause scenario, the effective process relating the two things is not a quantum channel. It's something that's not completely positive. I'm
not sure of the question that you're asking me.
The question is whether the causal discovery protocols rely on this phenomenon or not.
So when you say phenomenon, you
this
mean,
phenomenon that
so insofar as there is a kind of similarity between temporal and spatial that I think Katja-Reid captures in that work, then yeah, I think that's correct, if that's what you're referring to.
Yeah, so I mean, what I mean is that in general, I can talk a lot about quantum tomography without talking about what Katja-Reid did.
Yes.
And so the question is, can I talk about the approximation from partial tomography that you're doing? Can I talk about that without talking about Katja-Reid's work, or is it involved?
Yeah, it's been a long time since I've read that paper, so
okay.
I'm probably not going to give the correct. I mean, the main finding from that paper that you're referring to is what exactly?
The main finding is that there are quantum scenarios in which you can tell how much non-Markovianity, so to speak, is involved in your effective process. And the way in which you do this is by finding parts of your effective process that are not completely positive. So they are not allowed as temporal quantum processes.
I see. Okay, yes, definitely. There is a relationship.
Okay.
Yeah, gotcha.
So thank you again. And well, and so given we are a bit over time, should we still take a break or should we just go straight to the quick break? Okay, then a 5 minutes break. Okay.